Hello. Just going to walk you through the details of the example I just demonstrated. Just open up this version. Okay. Right, so we obviously need knowledge of the scene in order to be able to project onto it. Generally with projection mapping, this is either through getting a 3D model a priori of the scene and manipulating it and then projecting that back out onto the real 3D model, or live painting where we just select things in the 2D output of the projector and project onto them. So here what we do is we're getting this information from the Kinect. We've got the RGB map, which is the color image, the depth map, which is quite dark here, which comes from the second camera, the depth camera. Using the depth data, we can figure out the world position of each pixel. So that's the X, Y, and Z, represented here by red, green, and blue respectively. And also if we take the differential of these world positions, we can find the normals. And that's represented here with blue again as Z, red as X, green as Y. Right, so the way this calibration works is we want to find positions in the two spaces. Now the two spaces are projector space, which is what's being shown here, world space, which is what's shown here. And here's another representation of world space. If I hold up my board, you can see there's markers appearing here on the image. If I try and get that a bit square, it's easier to see. And those markers represent known points in 3D space because we can look them up in the Kinect. And the also known points in 2D space in the projector. So we end up with a correlation between where that point is in the projector and where it is in 3D space. We can look at where it is in 3D by finding the chessboard within the RGB image and then looking at that position within the world. These four images overlap in space. Okay. So the chessboard has got two effective outputs. One is where are my points in the image space of the projector, which is output here, and the graphic, which is output here. We can choose the spacing of the chessboard. If we have wide or narrow projectors, this projector is quite wide. It's wider than the Kinect, and therefore we have to choose to not fill the whole image, otherwise we wouldn't be able to see the whole chessboard within the Kinect if they're the same position. Okay, so the way this thing works is inside here, this is accepting the RGB image and the world image being this one and the RGB image being this one. It's accepting where the points are within the projector, and then it's got some controls. So if we look in here, we've got this data set which is going to get built up, and the data set is, if I just make a recording now and show you, right, it's the XY in the RGB image. Here we don't need that, we should use it to look up in the world image the XYZ. And here we just get a positive if we know a value for it. If we get too close, then the Kinect can't see the depth of it anymore, and you see it can't read the world value. You can see here corrupting down this end. That's the corruption we get over here. Right. So we take that, we pass it into these queues which store the data. This count tells us how many times we've stored. This waits for calm basically waits for when these world positions are calm, when they stop moving around. So if the average velocity of these markers is below a certain threshold for a long enough time, then we make a recording. So if I hold and it won't make a recording until it goes back up again, so you have to move it before you can do the next one. So if I move it in, wait 2 seconds, that should hit 7. There we go. Right, so the output of this part is lots of XYZs for the world space, or object space as it's called here, and lots of XYs for the projector. Now these are all the same values, so there's only so many unique, and then they repeat and repeat and repeat. Right, just hide this one. So after they come out of here, we've got the XYZs and the XYs here, which have been recognized, and they go into Calibrate Camera. The Calibrate Camera is the Calibrate Camera OpenCV function. It takes these input flags, it takes these inputs, the object XYZ and the image points XY. Now here what we're saying is that we've got a calibration object, which is a hypothetical object made up of all these individual chessboard positions, and therefore our world space XYZ gets transformed into gets stored as a big object, which is what we input into Calibrate Camera, and we have the image points XY of where they appear on the imaginary camera's sensor. So we know where they are in 3D space and where they are in the imaginary camera's sensor. And the imaginary camera matches up with our projector. Here's the resolution. We choose some options, so here we're choosing intrinsic guess because we can guess that it's a roughly 1-to-1 projector or something like that, and that's close enough to really start getting going with the projector. We don't want to fix the aspect ratio, even though most projectors you could probably tick that, because the pixels are square. If they're non-square pixels, you don't tick that. Principal point means the lens offset, so if your lens is making your image come up from the projector naturally, which is generally the case, you need to have that off, or if you use lens shift. Zero tangent distortion, we're presuming no distortion basically, so I've got that turned on. Zero tangent distortion doesn't fix the focal length, so it can change the zoom characteristic. Fixes the distortion on K123, which I've called here Ki, and doesn't use a rational model. I'm not too sure what that is. Okay, and then we've got all our data coming in. What we do is we hit solve over here, and that comes out here and it says okay. Reprojection error means it's made a model which is defined by the camera intrinsics, which is this matrix here, and the extrinsics, which is rotation and translation. And it applies that model to all these object points and calculates the image point. And then the average error between its calculated image point and the input image points is this reprojection error. Okay. And these just get passed out, so they can be used by the rest of the program. Just tidy this up. And then they come out here. And then this data comes out basically as view projection transform. And view projection transform is the extrinsics, which is your rotation and translation, multiplied by the intrinsics, which is the camera transform. So the view transform is the extrinsics essentially, and the projection transform is the intrinsics. And we can apply that view projection to our object. You can either choose to put it into the view and projection pins of your renderer, but since we have a few renderers, I've kept it tidy by just plugging it directly into the shader. So the transform is basically the view projection transform. And this shader here accepts the world coordinates in XYZ, normals in XYZ as well, and those are two textures, which are these two textures here, floating point textures, so they can go negative, positive, and outside the values of 0 to 1. And then, because we're working camera coordinates in V4, we have to transform the renderer often, because our renderer is generally -1 to +1, +1, -1, and here we have to say this is 0, 0, and that's 1280, and that's 800, so this comes in this transform here, which gets applied to T screen, which is a special transform that I added to the shader. Okay, it's accepting some other things in the shader, like which technique to use. If I just go to normals now, this is in projection space, you can see. If I turn off calibrate, you can see that's coming out down here from the projector. You can see it's coming out of the projector there. So we've got a few techniques. T preview is pass through the color value, but we don't have it connected. T light directional is a directional light mechanic. Light point is a point light source, and also on the point light source we're choosing to move the position and output that as a marker, which you can see come into view every so often over here. So that's like a LFO. Right, so inside the shader you can see what's going on. Here it's in PS light point. It's just doing simple lighting mathematics. Okay, just hide it up. Finally I can go to open an eye. A little bit messy here. Inside here it renders the world and the normals. And the normals have got one parameter here called spread, which is how many pixels left and right, up and down of the current pixel you use to take the differential. If you set this to 1, you get quite a noisy image because the Kinect doesn't produce smooth depth data, which jumps around a lot. So if you set the spread quite high, you see you get much smoother output, but then you get problems on the edges of objects. So here I'm just choosing 2. You could choose whatever you like. Okay, and you can have a look inside these shaders by clicking right-click. You can see how they work. This uses the good old hand-driven intrinsics of the Kinect from the Stanford guy. It's quite old. It's not necessarily very accurate, but since it's systematically true in the system, it should be cancelled out. Okay. Just add this up. So yeah, the shader comes out here, goes into the projector. There's 2 renderers for the projector. One is here, one comes out the bottom. That's just the preview here. And there's some preview elements in it, so layers for here and things like that. And that's basically the patch. So you can download that from GitHub now, and good luck. Bye-bye.